I can't get it to work. This is crazy. Can't get it to work. This is crazy. Oh, I think I got it. Can't get it to work. This is crazy. Oh, I think I got it. There we go. Can't get it to work. This is crazy. Oh, I think I got it. There we go. Okay, so I guess we can do this one of two ways. You can ask some questions and I can try to answer them, or I can just start from the top and walk through it all. Why is it echoing? Check, check. Check, check. Is that better? Check, check. Is that better? Okay. So, should we start from the top, or you want to ask some questions? All right. So, I guess I'll just start from the top now. All right. I'll answer Jetty's question here. Yes, it's always for categorical data. It'll be a 2x2 table if it is. All right. Let's start from the top, though. Okay. Sorry, I'm just making sure this is working. All right. So, where we started this year was defining variables. And we started talking about one variable at a time. We started talking about quantitative variables. From quantitative variables, we get means and standard deviations from those. So you want to think about the different graphical displays you would make with univariate data, one variable. So for quantitative data, you're going to use SOCs. That's box plots, histograms, dot plots, stem plots, ogives. For categorical data, it's going to be bar graphs, probably segmented bar graphs if it's a 2x2 table that you have to make a graphical display for, or a pie chart. You're not going to have to make a pie chart. There might be a pie chart. So really, bar graphs are what you might have to make for categorical data, segmented bar graphs. Quantitative data, you should be prepared to make box plots, histograms, dot plots, stem plots, and also interpret them. So these are about the linear changes to like mean and standard deviation. So measures of center are affected by both of these, addition and multiplication. but measures of spread are only affected by multiplication. So remember that when you're looking at univariate data, you're using SOCs. Talk about the shape: skewed right, skewed left, symmetric, bimodal, bell-shaped. You know, if you feel like it's a normal, you're gonna say it's approximately normal at best. You're probably better off saying it's symmetric, bell-shaped, and unimodal, and maybe approximately normal. Remember, you're just trying to communicate that you understand what you're seeing. That's really important. And you're looking for differences. Remember, if you're comparing two distributions, use comparative language. Look for differences. There's going to be differences. That's the point. If everything was the same, we're not really commenting on anything. But definitely comment on, use that comparative language. That's really important with this. And then we moved on to bivariate data, which is scatter plots and linear regression. And there's a few things you have to make sure that you're going to define. These things are definitely going to show up. And that's R, which is the correlation coefficient. Remember, when you interpret that, you want to talk about the strength, the direction, positive or negative, and it's always linear with R. Some of the facts about R you want to remember. Yeah, the PowerPoint is on Google Classroom. It's called the AP Stat Course Summary. So a couple facts about R that might come up in the multiple choice questions is that it's unaffected by changes in units. So if I convert from inches to feet, the correlation stays the same. Remember, the line of best fit would change, but how related they are won't change. If you switch X and Y, R will the correlation stays the same. And because you calculate R with means, it's highly affected by outliers, just like the mean is. So remember, if they ask you a question about would you use the mean or the median, use the median when there are outliers because it's a more reliable measure of center. So then you have R squared. Remember, that's the coefficient of determination or the coefficient of variation. You might have to define that. On the multiple choice section, you should look for that phrase, which is the percent of variation in Y that can be explained by the variation in X, or you can say it's the percent of variation in Y that can be explained by the LSRL with X. So remember that if they give you R squared and they ask what R is and you take the square root, it's technically plus or minus. Check the slope to see if it's positive or negative, or if you have the scatter plot, check the relationship, see if it's positive or negative. Make sure you know how to explain the slope. It's for a 1 unit increase in X. On average, make sure you get that in there. Y will increase or decrease by the slope. Of course, context your face off there. Y-intercept key there is make sure you get the word predicted in there. It's the initial value. Remember that the y-intercept doesn't always make sense in the context because it's sometimes extrapolation. So it might come out negative and not make sense. Make sure you know how to find residuals. Observed minus expected. Those questions, they usually give you a point, an x, y. And that's the y is the observed. And then you have to sub the x into the equation to get the expected. And then remember, jungle love, observed minus expected. It's also the numerator, the chi-squared equation. So you might have to do some regression in your calculator. Be prepared that you might have to make a scatter plot, whatnot. Make sure you know residual plot. So in the scatter plot, you're looking for patterns. That's good. Residual plot, you want randomness, nice variance. If it fans out at the end, you want to mention that it becomes less reliable as X increases. So this would be a bad fit on the left here. Not that there's a nonlinear. There's no pattern. It represents a linear relationship. Let's see, anything else about the bivariate data? I mean, there might be like an exponential model on there on the multiple choice. You interpret everything in context. Let's see if I missed anything up here. No, it's good for now. All right, so after bivariate data, we moved on to collecting data. How do you collect data? So some of the methods we talked about, you should know what these things are. They'll come up. Make sure you know the difference between an experiment and an observational study is a treatment being imposed. That they like to ask about that. So all the surveying methods, you should know how to talk about an SRS, which is also the same thing you would use to describe a random assignment. So remember, if you design an experiment on the open-ended section, you have to describe the random assignment, and you're using your SRS phrase that pays here. Just remember, if there's a multiple choice question, or if they ask you about to define what an SRS is, just make sure it's not that everyone has an equal chance of being selected. It's that every sample of size n has an equal chance of being selected. Um, just some sampling methods. SRS, systematic might come up. Remember, that's like every fifth person you would select. Make sure you can differentiate between stratified and cluster. Stratified should be homogeneous groups, think male and female. You do an SRS in each strata. Cluster, all the different groups, the clusters are heterogeneous. You randomize and select a few clusters, but you should survey every one of those clusters. And those probably show up in the multiple choice. It might show up in 2 or 3 of the open-ended as well. As far as types of bias, remember that there's 2 types of bias. There's sampling bias, which is natural variation, and then there's non-sampling bias. If you if they are asking on the open-ended section about things that would come under non-sampling bias, for example, response bias, the wording of the question, non-response, undercoverage, you also have to talk about whether you think that'll cause an over and underestimate. And make sure you're differentiating that bias versus bias in a statistic, in which case we want an unbiased, low variation, and in sampling distribution, as the sample size increases, bias stays the same, uh, but variability decreases. That's different than the bias we're talking about here. So make sure you differentiate those in your mind. If you use any of these terms on the free response, talk about also whether you think it's going to cause an over and underestimate. How do you know? You just got to think about it. Like, there was one question we looked about once that was you surveyed people by going to their houses during the day and asked how often they bake. And you would expect people who are home during the day to have more time to bake. So you would expect an overestimate because you have an undercoverage bias in the way you sample. Generally, you'll just be able to kind of glean it from what they're talking about, who you left out, and then what it would have caused an over and underestimate. Um, so then with experiments, remember there's 3 types of experiments you need to know about, you're going to read about potentially, or have to create. Completely randomized design is where you take your one group and then right away you shuffle people, you randomize into your treatment groups, your control and your treatment group. Think that's just from one group, you randomize. Another one you need to know is interviewers, the response bias as well, Ryan. The second type of experimental design you need to think about is block design, which is like stratified sampling in the sense that the block should be homogeneous. So think male, female, and then within each block you randomize. So if you did male, female, and you had a control and a treatment group, you'd actually end up with 4 groups. Women in the control group, women in the treatment group, men in the control group, uh, men in the treatment group. That's block design. And remember, you block to reduce variation. So if they ask you why you block, you do it to reduce variation in your results. And you also try to block by what you think would have the biggest differences between the groups. So if I was testing a drug, would I rather block by hair color or sex? I'd probably block by sex because I think there's more differences in how the drug will react between the sexes as opposed to between people's different hair colors. Um, so, ideally you would have a double-blind experiment if you were designing one where the people in the experiment and those who are uh, assessing it at the end uh, don't know who got which treatment. If you have to design an experiment, those diagrams are really good to do that. Remember, you have to describe the random assignment, and at the end, you have to describe what you're going to measure to see if there's a difference. Like, am I measuring change in blood pressure? Am I measuring difference in mosquito bites? Whatever it is. So, with experimental design, the three principles you want to know about: you want to have control for confounding variables. You don't want to put one plant in light and one in dark and use the old and new fertilizer because you won't understand if the difference is because of the light or the fertilizer. Um, uh, you want a replication, which is you want to do it on as many as people as you can, as many subjects, units, experimental units as you can. And randomization, which should create roughly equal groups. And it should also, if there are confounding variables between your subjects, hopefully it'll be evened out between the groups so it won't actually make a difference. And the last experimental design is match pair. And you're either going to see that where one person gets both treatments at the same time, like the mosquito repellent one on each arm. Always make sure you randomize which treatment comes on which arm in that case. Other way it'll happen is you take a break in the middle and you get both treatments. You need enough time to get back to the status quo. Also randomize which treatment comes first and second. Obviously, it's hard to blind that sometimes. There might be some simulations on number 6, maybe. And one of the things to remember that if you have to design a simulation and there's a 70% chance something, you're just going to assign numbers, 7 out of 10 numbers to represent what they want to have happen. So, like, I would assign numbers. If it was 70%, I would assign numbers 0 through 6 to success, 7 through 9 to failure. Probably not going to come up, frankly. Then we launched into probability. We actually did normal a little earlier, but anytime it says normal in a multiple choice question, you should think about norm CDF, inverse norm. It's coming up. Remember that two-way tables are really useful. No one's really going to use Venn diagrams on this. I mean, I would use two-way tables. So if it's any of those probability rule problems, see if you can use your two-way tables to organize it if you're getting stuck. If they give you something about conditional probabilities, like given of of the people who test positive, the test works 80% of the time. That's conditional probability. That's a tree diagram. Remember, you can always take the ends of your tree diagram and put them back into a two-way table as well. Right? I mean, because tree diagrams are really for dependent probability. If it's independent, it's really easy to do in a two-way table because you can just multiply the probability of A times B and get the overlap. When it's not independent or you don't know if it's independent, you got to go with the tree diagram first, and then you can take the tips and put them back into the two-way table. And then anytime it's this many out of that many, it's probably going to be binomial. Again, just check your bins that it's binary, that there's just success and failure, and that each trial is independent. There's a set number of trials, and that every probability of success is the same. Pay attention to that. And then the corollary to binomial is geometric. Anytime it says what's the first success, anytime you read that, you know it's geometric. Remember, the formula for that's really easy. It's just you want one success. So it's the probability of success to the first power times the probability of failure to the rest of the trials, which is k minus 1. So when you're combining means and standard deviations for probability questions, in a lot of cases, afterwards you might have to do like a normal calculation. So you might have to combine two means. There was one question that was in the free response about two trains coming together. Just remember that means will behave exactly how they think they'll behave. You add them, you subtract them, you subtract them. And with standard deviations, you combine the variances. So you might have to do that and then do a normal calculation afterwards. That's probably the extent of what you would see with that. You would use geometric PDF if I said, what's the Mr. Doris is a 70% free throw shooter. What's the probability his first free throw he makes is on his third try? That would be geometric. The K over N is a combination. You're never going to actually have to calculate that, but it's a combination. Oh, I hope my battery doesn't die. It's damn computers, you know. Then normal probabilities. If you're again, these rules are complements really important. Remember, anytime you see one probability, write two probability. PDF is for when it's just one number. CDF is up to including with binomial. Remember, if it's at least one, do one minus the probability of none. That might actually come up. Don't forget your addition rule. You might have to use that. You can always, and think about, you could use a two-way table to help you with that. And then probability distributions. Remember, these two bottom formulas are on your formula sheet. But if you put this into L1 and L2 and do one variable stat with L2 as your frequency list, it'll give you the mean and the standard deviation. Binomial. Remember, the mean and the standard deviation are on your formula sheet. I wouldn't expect to have to use the geometric standard deviation, but the geometric mean might be on there. Just the reciprocal would be. Continuous random variables, really the only one you're probably going to work with is the normal, chi-squared t. I really wouldn't worry about that. The sampling distributions, these are right on your formula sheet. I'm definitely going to use these at some point. Oh, these are what you use for minimum sample size. You're solving for n on these bottom ones. So if it's proportions, just remember that it's times the margin of error here. We get to confidence intervals real quick. I'll help you with that. So then we went to inference. We started with those sampling distributions. Make sure you're differentiating between the distribution of a population, the distribution of a sample, and the sampling distribution and which one they're asking you about. So you're not dividing by the square root of n. If I go, what's the probability that a single person is above 50 pounds? That's not divided by the square root of n, but you kind of are because the sample size is 1. If I ask you, what's the probability in a sample of 20 that that the mean is above a certain rate? That's a sampling distribution then. On the printout, if you get a linear regression printout, it's already divided by the square root of n. They call it the standard error, so that means it's already divided by the square root of n. As far as inference confidence intervals, let's see if I can find the formula in here real quick. Let me hold on a second. Hold on a second. Okay. So for minimum sample size, remember you're going to take the margin of error, and that's going to equal. So for the mean, it'll equal z star times the standard error. And you can solve this for n on the spot, or the formula to memorize is this. And basically you're just swapping margin of error and square root of n and squaring. Well, that's for means. And it's always a Z star. It'll never be a T star. Just remember, you always round up on minimal sample size. Um, and then for proportions, it's the margin of error equals Z star times the square root of P times 1 minus P over N. And again, if you just kind of swap the N and the margin of error in square, you'll get N by itself, or you can memorize this formula. And remember, if they don't give you P, use 0.5. And any question on the multiple choice section that asks you, like, where do you expect the most variation, and it's about a P, P close to 0.5 is the max variation for P. As you get away from 0.5, variation increases as you get to the poles of close to 0 and 1. So keep that in mind. So that's your minimum sample size stuff. Don't forget to, in terms of inference here, make sure you're for boxing everything. Oops, I don't want to say that. Four boxes, inference for everything. Define up here. What are you going to define? You're going to any P's. If it's two sample, P1 and P2, mu. If it's a match pair, mu of the difference like this, it should be one variable on match pair. And then you want your HOHA up here. The other thing is make sure you get your titles down, because in the bottom left box, we're not going to show work down there, so you have to put a title up. Conditions up here. In general, something about random. Use their words. Random sample, random assignment. Use their words and say that it's stated. And then something about the 10% condition. Check your N. And then something either normal for means. You want to write normal and say N is greater than or equal to 30 generally for by CLT, or if it's two sample that they're both.
Can you hear me? Yeah? Hold on. Let me pull the sorry, I had to switch computers. I thought I brought home my power cord and I didn't. Goo for me. So hold on, let me pull up the PowerPoint again. Hold on, sorry. Oh wait, sorry, wrong one. I need this one. Sorry guys. Hold on, I just want to pull the PowerPoint back up. Eat breakfast tomorrow, but not too much breakfast. Eat lunch tomorrow as well, but not too much lunch. Did everyone say hi to Iron Spider? Welcome. Helping the world tonight. That's not it. That's what I want. Sorry, guys. Coming in 2 seconds. Gotta download this. Open that up. Do one of these. Okay, I think I got it. Is this it? Are we back in business? All right, where was I? Oh, yeah. Inference. Okay. So let's start with let me hold on a second. I'm gonna pull up I'm gonna pull up the formula sheet, the inference sheet real quick. Okay, so hold on. Sorry, guys. Let's share this. Okay. So remember, in terms of inference formulas, no one sample Z. You're not going to see that. It's going to be a T if it's there. Looking at conditions again, random 10% normality. Make sure you know you can do it either by the population is normal and is greater than or 30 by the CLT or if they give you the actual data, sketch the distribution and declare it not overly skewed with no outliers. HO only have one variable. Make sure you define mu's if you write them here. So it's going to be a T. Don't forget to write your degrees of freedom. It is on the classroom. It's under exam stuff. It's there. You can hear me, right? Sorry. All right, I'll assume you can hear me. Remember, for a match pair t-test, if it's going to be a match pair t-test, they're going to give you a t-table with data that looks like it's matched up, and you got to ask yourself, is it matched up for a reason? And remember, some of the reasons it's matched up are the two pieces of data from the same person. We saw two different operating systems, and they were running different operations. So each number represented how fast each operating system did each task. That's match pair. That's where you're going to take the two lists, put them in L1 and L2, subtract them into L3, and then you're just running a t-test. Remember, when you write the HO on a match pair one, if you do get that there's only one variable here, and you only define one variable because it's just a t-test. I'm expecting probably it's going to be either, I mean, never mind. I'm not even going to say it because what's the point? Just be prepared for it all. Just remember that on match pair, you're looking for a difference. That's why it's 0. And then all the two sample ones, I would probably write, just be careful of the way, if it's one tail on a two sample test, which way that you set up your variables. That's going to be important. The z-test for the mean is not going to be on the open-ended. I mean, I might as well just declare it. It's not happening. The only thing that could possibly change your mind if it explicitly said the population standard deviation, but I'm telling you, it's not going to happen. Expect T. And for proportions, they're all z's. So what are you going to do? Just remember, on two samples, declare both n's are greater than or equal to 30. Both n's are less than 1/10 n. Both. Both did, and then remember, you can mix and match on the two sample ones too. So one could be greater than or equal to 30. The other one says the population is normal. I wouldn't expect that. Remember that bottom left box, you got to write what your test statistic equals, your DF. You should put your alpha in that bottom left box too. And then for confidence intervals, remember, these formulas are basically on that one page of the formula sheet. So they're kind of there for you. And again, we're not using these on the open-ended section, but these questions are going to, these formulas and setting it up is going to be on the multiple choice section. Just remember that in the bottom left box, if you're not going to show the calculation, you got to make sure everything's there. You're not going to get credit. So DFs, if it's a T, you got to put alpha down there always. Test statistic always. P-value always. Don't forget to title what your test is. I'm going to get to the proportions in a second. So remember, if n is greater than or equal to 30 is for means. It's different for proportions. Proportions, you're looking for normality with large counts. All right, remember, anytime it's an interval, you're always using p-hats on the intervals. And then on the tests, you're always using what's in the HO. So in the standard error, you use what's in the HO. So on a one sample, whatever the HO P is what you use in the standard error. And then on the two sample test, that's where you use the PC. And you also use that for the conditions. So, yeah. I mean, if I'm being honest about the 10% condition, they usually don't even score it. But it's good to put it there. If you're going to put it there, just say, it's 10%. essentially independent and declare n is less than or equal to 10, and either say you can clear it because you have the actual numbers, and if you have the actual numbers, use them, or because it's reasonable. 10% condition might show up as like a multiple choice question about what it's all about. But test statistics, the Z or the T. Yeah, that's right, Zach. P hat for intervals, P for the tests. Yep. And again, something about random. Remember, clear it for them. Remember, the whole idea of this is for you to communicate clearly what is the problem is stating. Be clear. It's stated. Remember, use their words against them. And then chi-square, goodness of fit's going to be a one-way table. Chi-square test of independence homogeneity, two-way table. As far as these expected counts, there's usually a multiple choice question where they ask you for an expected count. So just be aware you might have to use that. If you're running the actual test for chi-squared, don't forget that the calculator is going to put that in a matrix for you, the expected counts. You can just copy that matrix. Yeah, bottom left box, test statistic, p-value, alpha, df. Sounds good. And remember the difference between homogeneity and independence is homogeneity is multiple samples. It'll be real obvious. Just read the question. Or if there's random assignment, that's homogeneity too. Make sure you know how to calculate DFs. That comes up too. So make sure this one and the DFs and the expected counts. Yeah, make sure you got those. If there's a linear regression t-test, I expect it to be in a computer printout. In which case, I mean, I really don't expect it to be an open-ended question. If it is, you should just, know these, and then you're probably just going to clear them. So I wouldn't even worry about it really. But HO is always going to be that the slope is 1. Make sure you define that as well. This T is just going to be listed. You don't need to worry about this. Just remember that in the computer printout, it already is the standard error. DF's n minus 2. If they ask you for a confidence interval, you just take that slope from the printout, go get your T star, and multiply it by the standard error. Remember, all your T stars and Z stars are on that one page, the T distribution page. Bottom row infinity are all your Z stars. Yes, for a test, you're always assuming the HO is true. That's why the p-value you calculate, make sure you know how to interpret a p-value. That's different than the decision. The decision is going p is less than alpha, reject the HO because p is less than alpha. That's the decision. The p-value is given the HO is true, which is the whole condition we run hypothesis tests under. Given the HO is true, it's the probability of getting the result we did. In other words, the sample mean, the sample proportion, the difference, whatever it is, the result we did, or something more extreme, given the HO is true, again, by chance alone. So that's why if you get a result with a low p-value that happened by chance alone, you go, no, this didn't happen by chance alone. The explanation has to be the HO is false. Yeah, so this is all the inference stuff. Some other things that come up in inference, don't forget about type 1, type 2 errors. A type 1 error, remember, what you actually want from a hypothesis test is you want to reject the HO. Because rejecting the HO is the only time you actually get a conclusion, a significant result that matters. So that's what you're trying to do. That's why when you set up your HOHA, when you're trying to prove a claim, you always put it in the HA because you want to reject the HO and crown the HA. So a type 1 error would be to do that wrong. So a type 1 error is rejecting the HO when it's actually true. Whoops. And then a type 2 error would be the reverse, failing to reject it when it's false. And then you want to know the probability of a type 1 error is alpha, straight up. And the probability of a type 2 error is beta. And you're not going to have to calculate that. They had that on last year. It's not showing up this year. But you want to know the power of a test is the probability of rejecting the HO when it's false. In other words, it's the probability of getting a significant result when you should have. So you've actually proved something when that happens. So power is a good thing. And the thing you should know about power is that there's 3 things to increase it. And you should just understand the 3 things and then why you won't forget. So here again, if you increase alpha, it increases the power. Why does that make sense? Because the bigger alpha is, the more likely you are to reject. And so that's why it increases the power. The second thing would be increasing the sample size, because what does increasing sample size do? It reduces variation. Reducing variation pushes the 2 distributions further apart and makes it more likely you'll reject and increases the power. And the last one, which you can't control, but pushing your sample that you got further from the HO would also obviously make it easier to reject. Don't worry about what score you need to get if whatever. Just do your best. You guys are ready. I mean, you've seen all the multiple choice questions. Do you know your conditions? You're good. You'll be able to recognize the tests. Is it about means? Is it about proportions? Make sure you realize it when you do the proportion tests in your calculator that you're not putting the percentages in there. You're putting the raw counts. No, Emily, I'm saying that if your that sample mean you got was further than the HO, obviously it would be either easier to reject the HO. You can't control that. If you want to reject, you want your sample mean to be far away from what they claim it is. When would you use TCDF? You would use TCDF if they gave you a T test statistic or a T value and they wanted to know a probability. That's about it. You're never going to use PDF. Or that's right, Zach. Or normal PDF. That's true. Where were we? So I went through all inference. We talked about the probabilities. We talked about type 1, type 2 errors. Talked about confidence intervals. We talked about chi-square. No, not for sampling distributions, Enver. You'd use mu. Go look at the formula sheet. You use mu sub x bar and mu sub p hat and baby sigma sub x bar and baby sigma sub p hat. Remember that two-tailed tests and confidence intervals can be used identically. So if you rejected the HO in a two-tailed test, that would mean that the HO value would have been outside the confidence interval. And if you failed to reject on a two-tailed test, that would mean that the HO would have been inside the interval if you created it. Use PC only on a 2 proportion Z test to check your conditions and to create the test statistic. But remember, that's going to show up on a multiple choice question. If it was on a open-ended question, you don't have to show the work in the bottom left box, but remember, title everything. If you're given the p-value for a test, how do you determine the confidence level? That's not going to show up, but I think what you're actually meaning is if you get alpha, how do you determine the confidence level? So for a 95% confidence interval, that's alpha at 5%. I think that's what you're asking. To calculate the test statistic from you're creating the test statistic to get the p-value. That's not really showing up. What do I mean by the boxes? It means I'm an awesome teacher and I showed my kids how to make 4 boxes to set up their inference, and it's awesome, and they're going to kill it tomorrow. I don't know. I don't have an example right now. It's actually I probably do, but whatever. Um, well, I'm gonna go over. All right, I'll tell you what the 4 boxes is. So in the top left box, you would put your HO, and you would also define your parameters in the top left box. In the top right box, you would put your conditions in there and clear them. In the bottom left box, you would put your test statistic, your p-value, your df, your alpha. And in the bottom right box, you're going to bring it home. You're going to first link the p-value to alpha. If p is less than alpha, reject the HO. If p is greater than alpha, fail to reject the HO. Remember, that's all you have to write. Then in the second sentence, it has to be in context. There is not statistically significant evidence of a difference, or of a difference if it's a 2 sample or whatnot. If it's a confidence interval, remember you want to interpret the interval. Oh, I missed this. This is a good one. Interpret the interval is we are 95% confident that the true population mean proportion, that the true difference in the population means, the true difference in the population proportions is between those two numbers. Put those two numbers in context. Proportions, obviously, you don't have to. Remember that if they ask you to interpret the confidence level, the level is saying for 95% confidence, that means if you made many 95% confidence intervals, you would expect about 95% of those to contain the true population mean. Good to fit one on a table. All right, I guess I'm ready to open up the floor then. I think I pretty much talked about everything. I'm trying to think if I missed anything glaring. I can't think of anything right now. Level and an interval. Oh, the level is if I made many 95% confidence intervals, I would expect about 95% of them to contain the true population mean. The interval itself is saying I'm 95% confident that the true population mean or proportion or difference in means or difference in proportions is between those two numbers. Remember the distractors. Like, don't get distracted on when they ask you to on the. There's going to be multiple choice questions where they go, well, which one of these is the correct interpretation of either the interval or the level? Remember for the interval how they try to trick you. They try to trick you by going, it's the probability. If they say it's the 95% chance, no, that's not it. If they try to convince you that 95% of the data is in the interval, that's not true. If they try to convince you that you're trying to find the sample mean in the interval, of course the sample mean's in the interval, that you built it with that. You're trying to capture the population mean. You're not going to have to calculate power of a test, so don't worry about it. But if you would, you would get that X bar star and find the probability above. Don't really worry about that. It's not showing up. Let me see what else I can pull up from the from the classroom. Mm-mm. La la la. Let's go through this one. Don't worry about calculating the power of a test. Understand what it is and how you get it to be as high as possible. All right, hold on. Let's pull this one up. Okay. I mean, just some general stuff. This one is so important. Like, answer the questions that they ask. Don't be zombies. Like when they say, "Do the data show convincing evidence?" Use their words in the conclusion. Use their words. Answer their questions. Make sure you're answering their questions. Don't be zombies. And if there's a multi-part question where you can't get part A, make up a probability for B. If you use A and B, part B. That is important. Yeah, answer the question you're asked. Make sure, like, sometimes on some of the tests this year, you guys would write stuff and never actually address what the question's asking. Make sure you do that. All right. I went through all this. I mean, let's see. Anything in here worth remember, if you're not sure, use words like approximately. Yeah, context your faces off. Context on that free response section. It might be the difference between you passing and not passing. And the other thing to remember is that if they ask you to make a graph, you make it beautiful. I mean, that's for sure. Remember to budget your time on the free response section. Yeah, I mean, I think you're going to be good. I mean, again, to me, the hardest part of the whole test is probably some of the probability for people. But use your devices. Create a two-way table. Calm down. Try to use a two-way table to organize the information. If it's conditionals, start with the tree diagram. Can I create the sample space? Difference between lurking and confounding. They usually don't make that big of a deal about the difference between the two, and there's definitely more talk about confounding than lurking. Lurking variables are when the fact that the more firefighters are at a fire, the more damage is caused. But does that mean the firefighters are causing the damage? No, there's a lurking variable, which is the size of the fire. The bigger the size of the fire, the more firefighters that are there. The bigger the size of the fire, the more damage is caused. So when you go to correlate number of firefighters to damage caused, they correlate positively as well. The moral of that story is that correlation is not causation. A confounding variable is when you're trying to do an experiment and you can't tell if the difference is because of your treatment or because you didn't design your experiment well. Remember, my favorite example for that is old fertilizer versus new fertilizer, but you put one in the light and one in the dark. You can't tell if the difference is the light or the fertilizer. Mm-hmm. Mm-hmm. I mean, I think Zach can just run this session, actually. Yeah, just make sure the stratas are homogeneous and the clusters are heterogeneous. Anything else? Zach, you got to go read that book, Infinite Powers, Stephen Strogatz. I would recommend everyone read that book. Goddamn calculus, so useful. A link for this PDF? Oh, I don't know. This is in our Google Classroom. I'm not sure how to post it somewhere else right now. I'm sure if you Google, I don't know, AP stat tips for AP exam, I don't know. Oh, you read it, Zach? That's good. I want to read that. We should talk about it. Man, calculus. It's amazing. Extrapolation is where you make predictions outside of your data set, and those tend to be unreliable. Interpolation is when you make predictions within your data set or close to your data set. I don't know. Let's see what else is in here. I'm pretty sure I said most of this. You fool. That's wrong. You just lost points. Influential versus outlier. I like to say that outliers are against the trend. So if it's a positive correlation, an outlier would be against the trend. Influential points tend to happen further down the x-axis. So you could have an influential point with the trend and it'll unnaturally strengthen the trend. And then you could have an influential outlier, which would be down the x-axis and against the trend. What do I recommend going over tonight? I don't know. Make sure you know your assumptions. That's for sure. Your phrases that pay. Make sure you can interpret slope, y-intercept, r squared, p-values, that kind of stuff. Confidence intervals. Yeah, the conditions will be there, Emily. I mean, just remember, first differentiate is it means. I mean, if it's a two-way table or a one-way table, it's some sort of chi-square. And if it's about means and standard deviations, it's some sort of t. Just pay attention to how many samples. If they give you a match pair of data, check if it's match pair. And if they give you counts, this many out of that many, it's proportions. I gave you a sheet in class that had like a flow chart from the Stats Medic that was pretty good for how to kind of handle recognizing. Double blind, completely randomized design is the name of the design type, Michael. The double blinding is just something you could do in any really design, block design. Even match pair, although match pair is kind of harder. I mean, it's possible. It's definitely possible to just not know which treatment you got. A good example of that for match pair was we did two gloves with a new treatment versus old, and if you couldn't tell the difference, the person using them couldn't tell the difference, and if you could use the person evaluating not telling the difference, then that would be double blind. Don't worry about running the wrong test. You'll be fine. Should we draw graphs for hypothesis testing FRQs? You don't need to. Zach, you mean the conditions? Yeah, it is. If you mean the formula sheet, I don't know. I think that's on there too, actually. I don't know. I mean, like, guys, you're probably good at this point. Unless you have some specific questions, you're going to do fine. You're going to do just fine. Factor, level, and treatment. Okay. So factors and levels form the treatments. So like a factor could be the amount of light, high, medium, low. So the factor would be the amount of light. The levels would be high, medium, low. And then I could do fertilizer is the factor, and I'm going to do old fertilizer and new fertilizer. And then I just make every combination of those, and that makes the treatment group. So I could do like new fertilizer with low light, new fertilizer with high light, old fertilizer with low light, et cetera, et cetera. They usually don't differentiate necessarily between those, but that's the idea. I don't know what else I got for you guys. Don't worry about that, Jess. You're gonna select the right test. I don't know. I'll take one last look to see if there's anything worth opening up that I posted right now. I went through all that. I don't know. Eh. I mean, I guess I'll just hang out for a little bit here if you have any questions, but I don't know. I think I kind of went through it all. I guess I got to figure out how to make this private. I guess I could have made it private. I'm helping the world. Everyone wants to know stat. Everyone's striving for 5 tomorrow. Yeah, maybe we'll play some PS4 after the exam. I don't know. I don't have a PS4, so. One over P is the mean of a geometric. So, like, let's say there's a 10% chance of something happening, which is 1/10. I would expect first success to therefore happen on the reciprocal the 10th time on average. All right, I'm only giving you like 10, 15 more minutes here, and then I'm going to sleep. Oh, man, I don't know what I just hit. That's not good. Oh, no. Bad time for that to happen. All right, there it goes. All right. How do you identify binomial questions? Will be probably like, what's the probability of 3 out of 7? And geometric questions will be about first success. Why is the sum of the residuals 0? Because you got to think about what like a mean is. A mean is considered like the middle. The idea of it being the balance point is that the deviations from it on both sides are even. So if you just added up the deviations, they add to 0. That's why when we were calculating standard deviation, we couldn't just add the residuals up. We had to square them first to make them all positive. Probability flowchart. I'm not sure what you mean. Oh, right. Yeah, let me pull that up. I think it's in remind.com. Yeah, Dan, it'll save. Um, oh, it's so bad. Let me see if I can save it. Oh, I guess that'll have to do. All right, ready for the spiel? So when you have events, events can either occur at the same time. In other words, the probability of them both occurring is not a 0, or they can occur at the same time, in which case they would be mutually exclusive. So when they're mutually exclusive, the probability of A and B is 0. That's easy. When they're non-mutually exclusive, the probability of A or B depends on whether the events are dependent or independent. If the events are independent, that's easy. You can just multiply the probabilities together to get the probability of both. In that case, I would use a two-way table. If that's not true, if there's conditionals where things change, then I'm going to use this formula, which is basically means you have to use a tree diagram to find the probabilities. Remember the general addition rule, or is you add the two probabilities and subtract the overlap because the overlap was counted twice. That's why on mutually exclusive, the formula simplifies because there is no overlap. Remember the complement, anytime you hear a probability, you always hear 80% chance of something happening, 20% chance of it not. Any question that's at least 1, you should do the complement of 0. Standard deviation of the residuals is basically tells you the average error of the residuals. Yeah, I got to get deeper into infinite powers. Well, a two-sample z-test would be for means, but you're probably not going to see that. It'll probably be a two-sample t-test because you're not going to have the standard deviation of a population. Two proportion is for counts, 40 out of 50. I don't know, Chris, is that satisfactory on this? Mutually exclusive probability couldn't be easier. It's when it's not mutually exclusive that it gets interesting. And remember, independent two-way tables are easy. Dependent, got to use tree diagrams first. Yeah, I know, this picture's terrible. Let me see what I can do. This thing's like super grainy, but I can try. It's the best I can do. Sorry it's so grainy. No. No, there was one weird question, Varun, where they were trying to add a variable to another model, and so we were interpreting the residual plots as Duffs. But in general, if there's a question about residual plots, you're just looking for randomness for a good fit. So my answer is don't use Duff with residuals. Yeah, just for the scatter plot. Duffs. And remember, linear and non-linear. It'll probably be linear though if it's there. I'd have to imagine. When you interpret R, it's kind of like Duff's, except the U without the U. And the form is always linear. So basically, you're going to address the direction on whether it's positive or negative, and the strength based on how close to the poles it is. I don't want to go over the conditions again. I guess I can pull that document up again. I mean, it's, I don't know. I guess I'll pull it up. Yeah, there are your conditions. R is unit list. Crazy, huh? Dara, I'd start by making sure you bubble in your name right. That's always a good start. Make sure you budget your time on the for response section. 12 to 13 for 1 through 5, 25 for 6. Oh, I mean, I don't know, Tommy. That question was on there once. I wouldn't expect anything like that. It's a binomial test. You mean a binomial probability? I don't really want to go over that anymore. Binomial probability. I'm like losing it here. Binomial probability is when you're trying to do like, what's the probability of 3 out of 5 or something like that. All right, 10 more minutes and I'm out of here. And go to sleep, Emily. That's the great plan. It's going to do you well. Yeah, you know I love you guys. You're welcome. Anything else? Oh, um, I don't know where I can post this now. I guess I could post it. Hold on. I'm going to hook it up right now. I think I have it. Let me find it. If I can find it easily here, I'll send it to you. If not, look at that. It's your lucky day. Sigma x and S sub x. Sigma x is the sum of x. S sub x is the standard deviation of a sample. You are all very welcome. Do your best, and that's all that matters, really. Honestly. Hopefully, I'll take some more stat in the future. Don't worry about what percent you need to get a 5. Just do your best. My poor Mets got beat up tonight. It varies anyway. It depends how people do. Like number 6 last year was a disaster, so they didn't really count it. Bye bye. Anything else? All right. I think I'm done here. All right, let's sign off. Godspeed, stat students.